Okay, we've dealt with gates at length. Okay, now we're going to introduce other gates. It's just a different wiring of gates. Okay, in fact, it's actually a little bit of a pun. It's wired gates. All right, we're going to present wired gates now. What are these wired gates? Let's take an inverter. I need something to write with. An inverter. What we'll do is we wire these outputs together. Okay, that wiring. Now, if we have A there and B there, the active states or the high states, the active states for these inputs is actually give these inverters low outputs. If any of them is on a high, which is the active state, the output here will be low. That's what we mean. If we have A and B, if it's 0, 0, 0, 1, 1, 0, 1, 1, here the active state for B there will drive B to a 0. The active state for A there will drive A to a 0. The output of this output to 0. The active states of both will obviously drive this to 0. You have to note that if any of them is high, if any of them is low, if any of the outputs is low here, the other one will be held low, because you cannot, if you wire 0 to anything, it will drain that output. It will also drive it to a low. So if any of them is low, that output is low. Now if you consider this now, the actual inputs, the gate is the dot. That wiring there is the gate. It says you or you, I'll let you through. This is what decides what goes through. Now, if the inputs therefore to that gate are actually the inverses of A and B. Now, this would imply for 0, 0, it will be 1, 1. For 0, 1, it will be 1, 0. For 1, 0, it will be 0, 1. And then this will be both zeros. Now, if remember, any active state in the inputs here, in the input to the gates, actually means a low output for the gate, which means a low input for the what? A low input for this wired gate. Therefore, the output there will have to be held low. All right. So it means therefore, if you look at this, we are saying this is the OR gate. We are saying, however, it's an OR gate for the low conditions. All right. It's an OR gate for the low conditions, and if any of them is low, if not A or not B is low, then the output is low. So this is a gate whose output will be low if the OR state is what? If we have the OR state. We have but it's an O for the low. If any of them, if this one or that one is low, then the output is low. Unlike the previous OR gate that we're used to, where if any of them is high, the output is high. The inputs were active high for an output to go high. In this case here, the inputs have to be active low. The inputs to the gate have to be low for this to be low. Okay, so this is an O for the low condition. So therefore, if for the normal gate A, B, 0, 0, 0, 1, 1, 0, 1, 1, it was an O for the high condition, and we said our output would be Z. It follows therefore that in this scenario where the O is for low, for the output to be low, has to be not Z. So we'll call this output here not Z, because the output is actually low if the one or the other is low. So the output cannot be Z, it has to be not Z because the output is low. All right, the O is for the low state. Now, if therefore we want, so I'm going to put an inverter here, but since my output is an inverse already, the inverter always follows the inverted side. So our inverter therefore has to follow suit and point towards the inverted side, so that here we have our Z. In this case now, by placing an inverter there now, what we're actually doing now is we're actually changing. If our node Z was, this was 1, I need a pen. This was 1, if this was 0, 0, 0, because that or that was low at that point, and our output has to be low. It means, therefore, if you place an inverter now, our Z will have to be the opposite. Now you can see that our output now responds to the highs of the input. Okay, our output now responds as a normal OR gate. So this here becomes Z is equal to A or B. That would have been Z, not Z, this is now Z. Okay, this is now, you see how it's a OR gate, but it's from the wired situation. So it's a wired OR gate. So this will be our wired, let's name it there on top, our wired OR gate. I hope that was not very confusing. If we were to take the very same gate, let's go and take the very same gate and say, okay, how about we make the inputs lows, not A. Therefore, our inverter has to face the NOT, the inverted side. And then node B, our inverter if we did this, what do we have? We have here a scenario where our inputs, we don't have A, B. A and B are now here. Okay, but we started off with not A, not B. So if we had both zeros, 0, 1, 1, 0, 1, 1, that would imply 1, 1, 1, 0, 0, 1, 0, 0. Exact opposites. Now remember that because of the join here, if any of them is on a low, what does it do? It drives that what? Remember here, we said our input here is actually opposites here. The input to the gate was not A, not B. Okay. Now let's then say here we've got our inputs as A, B. There is A, B from the inverting of the original inputs, that side of the gate. Now our input to the actual gate, to the wired gate, then is this AB, and therefore our output Z here, our Z here, let's investigate. This will be ones, there's no zero, so that will be 1. Now that will be, because of the 0, it will pull the other one, they are both zeros anyway. So now you can see 1, 1 gives us 1, and the rest of it gives 0. This is the output of the AND gate. If you treat this as your normal input to the AND gate, that will be the output, that will be the normal output of the AND gate. So this here is equal to A and B. Remember, our inputs to the actual gate are actually these ones here. All right. So if we are to look at the wired gate, we have a symbol for the OR gate, and normally the symbol for the OR gate is what? Is a greater than or equal to sign. All right. It's a wired gate, so we also call it dotted gates. We put a dot there. We also call it dot gates or wired gates. It's the same thing, dot or wired. That dot there represents that wiring where the output stems out of. Okay, so any inputs that come in there, A, B, difference is there must be the dotting there. All right, this here, but remember the inputs are not the dotting, the inputs go to the what? This just says it's an OR gate, the inputs are actually inverted. Okay, the inputs to the actual gate here, this is one input, that is the other input, this is what is read by the dot. If it reads a 0, output 0. If it reads only ones, then output 1. So the reading is there, the inputs are actually the inverses. All right, very important to remember that. Now the symbol for this is the symbol for the dotted OR gate. Okay, the symbol for the AND again is dotted, so we place a dot there, and there is our Z, and this here, the inputs are actually just direct, because the input to the gate is what goes to the dot, so that's A and that's B. Okay, so I hope that is not all. The only difference there is what? Notice the inputs and notice the what? The dotting. All right, that is the major difference there. So I don't know whether that that complicates matters. I want to believe that it's somewhat not that difficult. Let me rather squeeze this together so that I can what? So that I can send it to the side. And have a little bit of space. I was in the middle so that you can see it. I'll put on the side so that you don't forget. And then I want to do more gates, more dotted gates. So let's do this together. Let's go to the next gate. Let's try and look at other gates. Let's look at exclusive OR gate. Let's have a gate like this. I will use two inputs, so I will use NAND gates instead of I'll use NAND gates, and I'm gonna do the O. Okay, I'll explain now. This here is going to be let's take I want inverted inputs, two of them, because what I'm trying to do is I'm trying to have a NOT A and a NOT B. Okay, from them I want, if this is a NOT A, that is going to be an A, because remember I want an A there and I want a NOT B here. I want a what? It's going to be a B here. Now I want NOT A to come, let me rather, to come down here. Oh, flip-flops are all over my head now. I was doing what I normally do with flip-flops. Okay, and I want the NOT B to go to the other gate. Not like a, but anyway it will work. So this here is obviously NOT A. That there is NOT B. Now it's wired together, so it still follows that if there is a 0 anywhere out as an output, it will pull the output of the NAND gates. If any of them is low, it will pull that, it will hold the other one low as well. So now the output here will be obviously A, NOT B went in, but this is the NAND gate. This one here with NOT A, B, but that's a NAND gate. This is going to say if there's a 0 here, I pull it down. If there's no 0, so that's an AND reaction. that will be an AND reaction, A not B, and not A, B. Then it's then and there. Now, if you look at this, this is a wired, what called the inputs. The inputs that came in are inverted, so it's an OR gate. It's a wired OR gate at this stage, but then we're using a wired OR gate. The output here is what? The output here is a NAND gate. Let's prove it. It's an exclusive NOR gate. This here will be an exclusive NOR gate. Let's prove it. What is this? If we say break this apart, that will be, I want to do this. This is A, not A. Double line on B, but it's O. B, double lines will fall away. And this one here is, we broke that line. So one line was left on A. This one was 2 lines, so it fell away. That one there, we break that line. It's going to be not A, so it's A. We break the line, we change the sign, it's B. And the other line remains on B. So when you expand this, this is not A will fall away, not A, not B. Okay, A, B, B, not B will fall away. So this here is the exclusive OR gate. Okay, this is what? This, as you can see, this is the exclusive NOR gate. Sorry, I mean to say the exclusive NOR gate. Inequality comparator, equality comparator, this is an equality comparator. So this is our exclusive what? This is our exclusive NOR. Our exclusive NOR using inputs inverted, using a wired OR. Okay, now we go on and say, to get an exclusive OR, we just need to say this is an inverse, this is the NOR, therefore the inverter faces the inverse, and that there is our exclusive OR. It will give us A, not B. We already know if that was true, it's going to give us the exclusive OR is the inverse. So, but anyway, let's prove it. A, not B, not, what am I doing? Getting carried away. This is still that. I'm rushing to the answer. This is still that. That is not A, B, but with that, and then we inverted, so we have the inverter now. So if you look at this, this is going to be equal to, break that line, what am I doing? Break that line, you have double lines there, because you broke the top line, it's going to be double lines. That sign changes because you broke that line. This is A, and you have double lines again there. If the double lines are taken away, that is A, not B, or not A, B. This is the inequality comparator. The other one was the equality comparator. So this is what? This is our what? Our exclusive OR gate. So this is our exclusive OR gate that uses what? A wired OR connection using NAND gates. Alright, so I don't know whether this is tricky or what, but anyway, let's try another exclusive OR gate, a different scenario. Maybe if people understand this, I will, just for space, I will remove this. Just me doing Boolean just to prove what's going on there. We don't really need that there yet. We'll see if we need it, but I don't think so. What I'll do is I will try and create space for myself there. I believe I still need to do 2 examples maybe before I can be happy, before I can satisfy myself that I have covered this expressly. This is, I did not give this a heading. Wired O, this was a wired end. I actually didn't name my things correctly. I did not mention the wired end here. This is wired end. I only named the wired O. There is the O, there is the end, and then this is the what? Exclusive O, using wired O connection and NAND case. As you can see, those are NAND keys. The wired O connection, and then using what? But we're also using NAND case. Okay, this is the exclusive O. Let's go into another one where I will do this. I will use O. Yes, I want to do the exclusive O, but now I'm going to use what? I'm going to use, let me use OR gates. So what I'll do is I'll take an OR gate, another OR gate, okay, then I will say let me put my inverters on the one gate. I want inverted inputs. Okay, let's have not A, not B, that will be A, that will be B. So our output here, there has to be wired, it's a wired gate, wired, okay, there is our output. Now we take those ones and we feed them to the other one, okay, and you say this is not A, this is not B. So this here is A or B, this here is A, not A, or not B, and it's wired together. So 0 will bring them down. Is what only one ones can survive. So it's an AND. An AND function here. This will be A or B, not A or not B. Now again, if you apply your thing, your De Morgan here, you will see that this is the same as A times not A falls away. A times not B, A not B, and then B times not A, not A, B, then B not B will fall away. As you can see, this is also our exclusive OR gate. Now, what have we used? We have used OR gates, okay, and we've got, it's a wired connection. So I don't know whether this is difficult. Let me try something else. Let me use let me show you something. Let's take a NAND gate. Let's take Z is equal to A, B, NAND. Using De Morgan here, we see that this is the same as what? This is the same as not A or not B. We break the line, we change the sign, it becomes O, and this is what we get. Now, if I use that, if I use this reasoning here, what can I do with this? I can say, I can have my OR gates. And I can say, if I invert the inputs to an OR gate, I'm as good as having a what? Okay. Alright. So I'm as good as having, if I invert the inputs, this is as good as using NAND gates. This is as good as NAND gates. Now, okay, this is me using NAND gates. Now, if I were to do the same and say, NAND gates, if I were to do this and say, got one, wait, I don't like this one. Okay, and I say that is my node A. My gate is facing that way. This is my node B. And I say my A here goes in with my, I think I've messed it up here. I've messed it up. My A here goes in with my, I wanted to go in with my B. I wanted to go in with my B. I've messed it up here. I've messed it up. This must go up. Okay. If that's beautiful enough. This is A, B, oh, not that. Okay. This is my inverter. I'm hoping that is not looking, okay. Let's say this is A, this is B. Again, I've done that. Forgot to take the pen. This is B. And this is not A, not B, not A, not B. What do you have here? You've got not A, O, not B. All I've done is swap this. It's now going the other side by putting inverters. These inverters here are going to make this A, O, B, because not A is inverted and it's a wire gate, and that there has to be A or B starting with the bottom, and not A or B, and we've seen how this is going to give us obviously our exclusive OR gate. So I can argue that it might not seem like it, but we've used NAND gates. These are an OR gate with inverted inputs is actually a NAND gate. All I did was change this. This is what I did here. I changed this to OR gates. Alright, so I don't know. I've covered most of the work that I want to cover. Let's hope that you understood. Try and go through it again. It probably is a bit fuzzy. Maybe you didn't get it as easy as I thought I tried to make it. So let's meet again for the next one. Hope you enjoy it.